In this video, we're going to be talking a little more about flows. So first, let's just remind ourselves about what we were talking about last time. So does the following graph admit a nowhere 0, 6 flow? Okay, so first of all, nowhere 0, remember that means that none of the edge weights are allowed to have a 0 weight. And 6 flow just means that all our weights, the absolute value is strictly less than 6. So we can have plus or minus 5, plus or minus 4, plus or minus 3, 2, 1. Any of those is fine. So let's start by just putting some directions on these. And again, like we mentioned last time, the direction doesn't really matter so much. So let's see if we can do this. You might want to try pausing the video and seeing if you can do it yourself. But let's just throw some on here. So let's say this is 2 in, 1, 2 out. This is 1 in, negative 1 in, make this one balance. So that means this is 2 out for a grand total of 1 out, which means that this should be negative 1. Okay, and so let's just say this is 1 in, 1 in, so we're going to need 2 out, 2 in, 2 out, and let's check to make sure this balances. 2 in, 1 out, negative 1 in, so yes, that's all fine. Okay, so these calculations will take some getting used to. But this represents a nowhere 0, 6 flow, and in fact it represents a nowhere 0, 3 flow, right? Because our biggest edge weight, the absolute value, is only 2. So if you go up from that, that gives us 3. But that's fine. The answer asked for a 6, or the problem asked for a 6 flow. We gave a 3 flow. That's perfectly fine because a 3 flow implies that you have a 4 flow or 5 flow or 6 flow or 17 flow or 38 flow or any number larger than 3. Okay, what about this one? So this graph in red, you may want to pause and ask yourself whether this has a nowhere 0, 6 flow. It turns out here the answer is no, it doesn't. And why not? The answer is because of this bridge. Okay, so if we think about putting a direction on this, you can imagine a flow is really like, water moving through pipes is the right example. You want the flow in to be equal to the flow out at any given vertex because you don't want to stress the joint of the pipes and have it blow up if there's more water coming in than going out. Well, a bridge sort of takes that idea, but we're sort of zooming out a little bit. So instead of looking at a specific vertex, look at the two pieces that erasing this bridge creates, right? So we've got this piece on the left and then this piece on the right if we erase this bridge. Now there's water moving around over here and then there's water moving around over here, but if water is only moving in this direction between these two pieces, eventually all your water is going to be in the triangle, right? And that's no good. For a flow, we want everything to sort of be in balance and constantly moving through the system. So if you have a bridge, it has to have weight 0, or else, right, all the water is going to be collecting on one side, whichever direction the bridge is oriented in. Okay, so bridges are not good for nowhere 0 flows. They're fine for flows in general, you just put a 0 on them, right? But if you want nowhere 0, that's not going to be good. Okay, so let's think about the more general version of what's happening. So here, this bridge is an edge. If you just remove one edge, it disconnects the graph. But you can think about a bond, which is just a minimal edge cut. So it's not necessarily a single edge, it's just a small number of edges. So for example, in this graph, here's an example of a bond, right, the bridge. But you also have several other 2-edge bonds. For example, if I delete both of those, right, I'll isolate this vertex. Or if I come over here, right, there are, of course, these types of bonds, the ones that move, that isolate just a single vertex. But then there's also the type that sort of runs across the whole graph. Right, removing those 3 would also disconnect the graph. Or similarly, right, in this last one, you have 2 edge cuts, right, like these degree 2 vertices, if you remove both of those. You also have 3 edge cuts, so maybe you do something like this. That would disconnect the graph, right? Or you can also have straight across, right, so like this would disconnect the graph. Or right down the middle, all these horizontal lines, right? You could just take all of these, and that would also be a bond. Okay, so bond doesn't mean the smallest size possible. It just means that you have a set, and if you put back any one of those edges in the set, you would reconnect your graph. Okay, so those are some examples of bonds. And a bond is the generic version of a bridge. So if you consider the fact that a bridge has to have a flow of 0, then if you think about a bond, the net flow across a bond also has to be 0. Okay, so let's see what we mean here. Assign a nowhere 0, 6 flow to the following graph. We're going to do this one, and then we're going to do another one. So this idea that the net flow across a bond has to be 0 can help you when you're building these things. So for example, let's say we start by doing, I'm just assigning some sort of random edges here. Okay, so let's say we start by putting a 1 on this. Well, now immediately we know the edge of this, we know the weight of this edge. Because, right, if you think about what's happening here in this graph, so let me draw. If I consider this edge removed and this edge, that's a bond in the graph, right? I've disconnected it. And if I put back either of the edges, I reconnect it. So since I have 1 moving in this direction across the bond, that means this has to be moving 1 in this direction across the bond. So this has to be a 1. So not only are you trying to balance at every vertex, that means that you're also balancing across every bond. So that's another way to help you sort of figure out what these edge weights are supposed to be. Okay, so then maybe, for example, I choose this and say it's a 2. Okay, so let's look at what's happening over here. Now, of course, you could balance this by thinking about what's happening at that vertex, right? Because now 2 out of the 3 edges have been assigned, so we know what's supposed to be happening here. Another way to think about it would be to consider, okay, if I remove this and this, that means that either one of these is going to form a bond. So if I say, do this edge, now I'm looking at these 3 edges, the net flow across those 3 should be 0. Well, right now, I have 1 moving to this piece, and I have 2 moving to this piece, which means that this should be a 1. Okay, and it is. And similarly, if I think about being 2 in, 1, 2 out. And here, right, if I had done the same thing, I would have realized that this needed to be a 1. Okay, so, or 1 in, 1 out. Or if I come back and think about, right, instead of deleting that that upper edge, if I deleted this one, right, then I've got 1 in, 2 out, and I'm going to need 1 in, which is exactly what we did over here. So thinking about bonds is just another tool to help you figure out what the edges should be. Okay, so similarly here, if I do, say, 2 on this, then that's going to be 3 in, 3 out, 3 here, 3 in, 3 out. Okay, so this is fine, right? This is, in fact, a nowhere 0, 4 flow because my largest edge weight is 3. But again, having a smaller number is fine, right, because it implies the larger kind. Okay, so let's just do one more of these. So maybe this graph here in teal. So again, you might try thinking about doing this if you want to pause and do it on your own. Okay, so we'll start doing ours. So I'm just going to assign some sort of random edges here. Okay, so first let's think about, maybe we just make that a 1. And maybe I'll go ahead and draw another sort of replica of my graph over here so we can be thinking about bonds. Okay, so if I imagine this edge being gone, that's the one I just put the weight on. Well, now I could go ahead and just go straight to this, right? And right now I have 1 edge or 1 weight going this way, going to this piece, and so I need 1 coming back to this piece. So 1 here. Okay, or I could consider, let me erase here. Instead of taking this edge with this one, maybe I take this edge instead, right? Which it says that since I've got one going away from this vertex, I need one going in. But now look, my direction doesn't match that way. So instead what I do is give it a negative weight, right? So one in, or one out, negative one out. Excuse me. Okay, so if I'm thinking about assigning edge weights, you can think about what's happening at individual vertices, but also to help you figure out what's going on, you can think about these edge cuts, these bonds in the graph. Okay, so let's go ahead and fill in the rest of these here. So maybe this is 2, so then I'm going to have 3 going in, 3 going out. And again, you can see if I look at this bond, for example, straight up and down these 3 edges, I've got 3 moving right to left, and then 1, 2, 3 moving, or rather I had 3 moving left to right, and then 3 moving right to left. And then maybe I put 2 going in here, 2 going out here, and now I've got 5 going in. Oh, so maybe I should erase these. So I'm lowering these because it would have forced me to choose a number at least 6 if I had done it that way. Actually, it wouldn't have. Let me go back. I'll just do it the way I was originally going to. So let's say these are 2. And then let's make this a negative 2. Okay, so then I've got 2 going in, negative 2 going in, 3 going in, 3 going out, which means that this should be a 3, 3 going in, 3 going out. And let's just check this vertex and see what's going on. So maybe we'll think about in and out for this vertex. So in, I've got 3, and that's it. And then out, I've got 2, negative 2, 2, 1, right? So 2 plus negative 2 plus 2 plus 1, which is also 3. Okay, check. So this one works. In fact, this is also a 4 flow. Okay, now, I was asking about 6 flows. Well, why am I asking about 6 flows specifically? Why not 10 flows or 3 flows or whatever? Well, if you play around, you might convince yourself that this doesn't have a 3 flow. There's no 3 flow on this graph. Or it doesn't have a 2 flow, for example. Similarly, this one up here doesn't have a 2 flow. So we want to think about what is the best possible K that we can say this graph definitely has a K flow. Or more generally, we want to think about the best possible K, meaning the smallest one, such that every single bridgeless graph has a K flow. So that's a problem that several people have worked on. So how big does K need to be to guarantee that every connected bridgeless graph admits a K flow? Right? We're not allowed to have bridges. We know that, right? If you have a bridge, it's got to have a 0. So, so this should be a nowhere 0 K flow. Right? That's why we're insisting on no bridges. And we want a K that works no matter what. Like if I give you a graph that has 10,000 vertices and 15,000 edges, or 30,000 edges, what K will work for that graph? Okay, or maybe it has 1 billion vertices and 100 million thousand edges or whatever. I mean, like make up whatever numbers you want. We want it to work for every connected and bridgeless graph. And it turns out the number's not as big as you might expect. I mean, so maybe you think, okay, yeah, if you're allowed to use up to 100, maybe that will always work. But it's actually much, much less than that. So a French mathematician named Gégé, looks like Jaeger, but pronounced Gégé, solved that, figured out that this number's it's not big, it's not even double digits, it's 8. So every connected bridgeless graph admits a nowhere 0, 8 flow. Okay, so that's pretty surprising. You don't need a very big number to make sure that you can get a flow on a graph. And in fact, a few years after that, Paul Seymour proved that it's actually not 8, it's 6. Okay, so this is why I've been using 6, because you can always find one that is 6. And in fact, it's widely believed, there's a conjecture, which means it's not proved yet, but someone thinks it's true, by a guy named William Tutt, very famous mathematician, that every connected bridgeless graph admits a nowhere 0, 5 flow. So we know that if this works, this is the best. There's no way that you can go to 4 because there are known graphs for which 4 doesn't work. But no one's been able to find a graph for which 5 doesn't work. So a lot of people think that 5 is the answer, but we haven't proved it yet. But we do know that 6 will always work. So in the last video, I'm going to give you a sort of another construction to explicitly create a flow on a graph when it's planar.